Hello, in this video we will talk about classifying MNIST handwritten digits using PyTorch. So we know PyTorch is a Python module or package for deep learning. So it works with setting up a neural network model for machine learning. So this is very simple or simplest neural network because here we have only one layer for the neural. So this is called hidden layer. And this is coming in for the feature. For example, if we want to classify digits 0 to 9. So here output their feature or the neurons. This output layer has 10 neuron. And we can set arbitrary number for the hidden layer, for example 16 or 20 or 10. And this is the coming in feature for one image. So one image coming in, their feature, because image has pixel, right? So pixel is two-dimensional, and we usually will flatten this pixel in one dimension. So this is for one image's feature like a NumPy array or one-dimensional array. So this is tensor, then flow to this layer. So each neuron in this hidden layer is like an operation. And this line, all the line can see this is full connected. So we call this a full connected neural network. So each neuron, each operation connected with each feature, and same as each output of this layer connected with next layer. So here is the output layer. And this operation includes the multiplication of the weights times the feature, then sum together, then plus a bias. Then we activate this result with one type of nonlinear activation function. So here we use one called the Relu activation function. So after this activation, then the linear input becomes the nonlinear output, such that we can model very complex data, for example, image or the text. But this is the simplest full connected neural network because there are more advanced neural network, which we will not talk about in this video. So next we will go to Python to train a such kind of model with two neural layer, two hidden layer. And you can download this file from this GitHub link. And we have also a website for Python and R training on weekend with a paid course for $3. So we go to Python, and from this file, you scroll to project 2, classifying MNIST handwritten digits. So first part of the code, we will get the data from Torch Vision. Of course, we import this package first. So we import this package. Then we move down to this project. So we load the training data and test the data for MNIST, because this data are already made from Torch Vision datasets. Then we set the batch size. So because they are very large data sets, and we will set a batch size 64. So for each update of the weights, we will use this size of the data. So the computation cost for each iteration contain many times of batch size, right? So for each update will be easier because matrix multiplication is smaller with 64 batch size. Then we use a data loader function, a data loader class in PyTorch. So data load is to load the training data and create as a batch size loader, then shuffle the data. Then after this operation, then we can train the data and batch by batch. Then next part is to set up the module. So we first will define two numbers, 32 and 16. So this is the neural number for these two hidden layers. And image size is how many features. So here we use the shape of the first image. Then image size is these three items, because by default this image is loaded by three-dimensional size feature, because this is for the channel, this is for the height, and this is for the width for the image. So we multiply these together. So this is 28 and this is 1 and 28. So the total is 724. Then first layer is the flatten. So we have said we will flatten these three-dimensional features into one dimension. Then we will use a loop for each hidden layer. So for each hidden layer, we will set up a linear. So this linear layer is the full connected layer with the input size and output size. So for the first hidden layer, input size is this image input size. If we look back here, so this is the first layer. Input size is the feature, how many features. So here now is 724 pixel, and this output size is the hidden layers number is 32, right? Then so we append this layer to the all layer. All layer is the first layer. Currently is just a flattened layer. So we append this layer, this neuron layer, to this first flattened layer. Then next we will append and Relu layer to this neuron layer. Then we will set the input size is the hidden size because this hidden layer, and next is another hidden layer. So this hidden layer's number will be income size for second hidden layer. That's why we will set input size is a hidden unit. So this loop will have to run. Then we will see how it is going. So this is done. Then we will set a new layer after this second hidden layer. So the new layer is just define the output number is the 10 digits, because 10 digits from 0 to 9. So we will have 10 neurons for this layer, and this is input size for the last hidden layers unit. So next we will use the sequential to all these layers together. We'll set up this module and we show the model. So you can see the model now. Sequential, the first So this layer called 0 in this model. With flatten, we start at dimension 1 and dimension. So we just did one row vector like. Then the linear from 784 and output is the hidden layer. First hidden layer 32 neuron. Then Relu layer activation. Then the second linear layer from 32 neuron to 16 neuron hidden layer. Then with another Relu nonlinear activation to this layer. Then the last layer is linear from this neuron number to the output 10 digits size. Then before we train the model, we will set up loss function. So the loss function is cross entropy loss. This is for classification, for the multi-class classification. Then we set the optimizer. Type is Adam optimizer with a learning rate 0.001. So this means the parameter. How many parameter? If we look at this, each line is a parameter for the weight, right? Each line is a parameter for the weight. Of course, here we'll add BS, add BS, add BS, 3 BS type. So all the lines together will plus BS, 32 BS here, and 16 BS here, and 10 BS here. So this is the total parameter number, and will be updated during the training. Then we will set up the training process. We set a random number generator seed, and we set a 20 epochs. Then for each epoch, we first will create accuracy for the training is 0, and for each training data loader, we will take a first batch for the X and Y. So the batch for each epoch, we will have multiple batch. For example, if we have 64,000 examples in the training, then the batch size is 64. So which means we will update the data 1,000 times for each epoch. Because in each epoch we will take examples, not whole example one time. We will divide examples into batch size. So the first 64 examples in the training, then we update the data. Then next 34 will update the parameter, right? But we will save how many correct for each batch size. Then we'll add in one number for accuracy, So you can see for the X batch, Y batch in training data, then prediction is the model for the X batch, because we will get the prediction of X batch incoming and with the current weight parameter. So this is the result for prediction of the Y. Then we will use loss function between Y batch is the real observed value, observed digits, and this is the predicted digits. Then this is difference is the loss function. Then we will loss backward. So back propagation is for the optimization process in the neural network. And we will set optimizer step, so which means this will be running update. And we will set 0 grad after each running. Then we'll take out how many correct for each batch between the prediction and the Y batch. Then this number summed together is the accuracy for the training. After running, we divide it by the length of the data. So this is the mean accuracy for the training in each epoch. So we run this part of the code. It will take several minutes. So my computer has a RTX 3060 GPU card. So you can feel it has many parameters to be updated. So it will take a little time. About 10 seconds for 1 epoch. You can see each epoch, the accuracy is increasing from 0.92 to 0.96. Still increasing. Still increasing, now almost 0.98 for the training data accuracy. So for the time limit, we only train 20 epochs. And you can see if we train more epochs, and the accuracy will be almost 0.99 and close to 1. So the model finished the training, then we can use this model to predict the MNIST data for the test data, which part of the data not used in the training. And of course, we can also calculate how many examples in results for the test data equal to the real digits. Then we print out the accuracy for the test data. So the test data's accuracy about 0.96. So a little bit over 15 for the training data, because they are a little bit 0.02 for accuracy difference between training data and the test data. So we only show the very basics of using PyTorch to train a neural network for the classification, and with the full connected layer. So this is the full connected layer. And of course, there are more advanced module for computer vision image. Thanks for watching.